Hi everyone, welcome to a special edition of our probability seminar. Special yeah. So what's going on? I think it's okay. So today I have the pleasure of introducing Oren Louidor, who's visiting from Israel. He's from Tech University. He was in the CMM school last year, so I guess you know him pretty well. Oren, yours.
Hey, thanks for the invitation. Santiago starts to feel like home away from home. This is joint work with Maximilian Fels, who's a postdoc in the Technion, and with Lisa Hartung, professor at Mainz. And I'm going to talk about the branching random walk, conditioned to be positive. Okay.
Maybe I have to
try everyone. Okay. So here's a quick outline. I'm going to tell you the setup, then the motivation, then some previous results, then the long session of our results, and in the end some post ideas. We'll see how much I will get. Okay, so here's the setup. So you take the binary tree of depth n, call 0 the root and L the leaves. Okay, x kind of in absolute value will be the depth of the vertex, and x minimum with y is a common ancestor. Okay, and then I'll take the edges of my tree and assign IID standard Gaussians to them. And then given a vertex anywhere, the value of h on that vertex is going to be just a sum along the path from the root to x of these edges. So the sum of the edges from the root to x. Okay, and x is known either by the name of branching random walk. So you can think of it as a so I think of h as a field indexed by the vertices of the tree. And you can either call it the branching random walk with Gaussian steps and binary branching, or if you want to be more fancy, you can call it the Gaussian free field on the tree. Okay, and it's not difficult to see that if you're summing Gaussians, then what you get vertex x is just the center Gaussian with variance x, and the covariance between the value of the field at two vertices. Well, it's just because of independence of these edges, it's just the variance of the joint path, and the variance of the joint path is just the height depth of the common ancestor, which you can also write like that. Okay, so any questions about the model, because it's fundamental for the remainder of the talk, and what we are going to care about is this event. So the probability that all of the leaves, so it's a branching random walk where all of the leaves are positive. And okay, what we will care about is not really along the way we'll also find asymptotics for this, but we really care about what happens to the field when you condition all the leaves to be positive. Okay, so that's the behavior under the condition. Okay, so why do we care about this? We care about the tree because we care about this object here. So you can, okay, if you want to be more fancy, you can write the law of this branching random walk in this complicated way. It's just the same. Okay, so let me just give you some, okay, let's interpret this. So just says that I'm putting the root. Okay, so this is the density of the field. You can kind of see that it's a Gaussian density. Forget about this for a second. This is just a quadratic term. So you think of h as, in that notation, you can think of h as a vector indexed by, so this is kind of this is the component, the x component of the vector. Kind of a slightly, take some time to get into this notation. So this is okay, so it's a okay, so you can see that this is a density of vectors indexed by the vertices on the tree. That's a quadratic form, so it must be a Gaussian. It's a normalizing constant. Okay, so this is the, okay, and then I'm putting, so this is the density with respect to the Lebesgue measure. This is just as Lebesgue measure on all vertices which are not the root. And at the root, I take a delta measure at 0. So I want the root to be precisely 0. And this is just captures all the IID edges. Okay? So that's kind of another way of writing this, or in a more economical way, you can write it. This you can think of. You can somehow introduce the gradient. So you can write it as the gradient. Okay. And so here's an economic and fancy way to write the same thing as before. The reason that I want to write it like this is that if now you can take other graphs, not just Tn, but you can take any graph and any boundary conditions, not just so you don't just maybe insist that the root is 0, but maybe other vertices. And if you take, for instance, instead of Tn, you fix a box of some side length, so Dn, some box of side length n in Z2, and instead of the root, you insist that outside of the box. So if you put the delta mass outside of the box, so here you put the box without the boundary, here the outside of the boundary of the box is set to 0, and then you look at the random surface whose density with respect to the Lebesgue measure on the box is exponential in the Dirichlet energy, in the square of the gradient. And now this is okay. And as I mentioned before, this family of laws is called the Gaussian, discrete Gaussian free field. If you do it on the box, you get this. Okay, and here, okay, and here maybe this question of having, so before I'm going to talk about is what happens when you condition on all the leaves. If you were doing this on a surface, you would want to condition maybe the surface to be positive, or maybe the bulk of it, maybe something inside the surfaces, whatever the analog of the leaves is. You can also, by the way, you can also in the talk that you can also replace leaves with conditioning everything to be positive, and essentially nothing will change. Okay, so in the surface, the planar analog would be conditioning this field to be positive. Okay, and that has a physical. Okay, maybe before I get to this has a, so conditioning this to be positive has a physical interpretation. I think it's written in the So okay, the first bullet says that this is the Gaussian free field. You can replace this with some other more general surfaces where you replace this potential here. So from being the square potential, the Gaussian potential, to something else. Then it's called Ginzburg-Landau fields. This interface is kind of a canonical of random interfaces. One thing that the physicists use it for is to model the interface between two phases or two materials, one say in liquid phase and one in vapor phase. And then conditioning things to be positive, for instance, says that you kind of confine these two phases of yours, this material, inside some container, and so the interface cannot be negative because there's the flow of the container. And so it's kind of studied extensively. So any questions? Yeah.
Do you study this in tree because it's simpler than the finite domain?
Yeah, so I'll say this in a second. I'll get to this in a second. Yeah. So what is known about, let me start from, so this is motivation, let me start from the two-dimensional and then I'll go back to the tree. So what is known about the two-dimensional case? I guess the state of the art is still dates to, as far as I know, to 2001, where there's first order. So first of all, there's first order asymptotic. So the probability that this creature that we just saw before, that this guy is positive in some subset. Okay, so let me state it more formally. I take the square, I take the discrete Gaussian free field on the square, this graph that we saw before. Then I fix some open domain inside it. And then I require that the field is positive. I think I'm not using this. The field is positive. But I need to change slides. You insist that the field is positive in a subset of the domain. Discretized, and everything is discretized by n. So and you scale this set by n. So now it becomes a subset of the of the box of side length n, and you want this to be positive. And first order asymptotics tells you that the probability of this is log n squared times, so it's e to the minus log n squared times the constant 4g, and then the capacity of u in v. Let me not get into this, I might get to this later. So some constant that depends on u and v. And moreover, they showed that under this conditioning, so if you're conditioning this object to be positive in the bulk, in this subset, then it lifts up by an order of 2 squared of g log n. So this whole, even though you just conditioned to be positive, it actually lifts up quite a lot. Not just positive, it lifts up to level log n. And kind of you get first order asymptotics in probability. That's kind of what he says. So the first order, the probability that it's 2 squared of g plus g log n or minus g log n goes to 0 as n tends to infinity uniformly. Okay, so it kind of lifts to that height. And why?
Zero boundary condition.
Zero boundary condition. Yeah. So this whole thing kind of, okay, this effect is called entropic repulsion. I'll get to this later. So this whole thing kind of lifts up dramatically, way more than what you want. Why 2 squared of g log n? Well, that's how they, okay, so in order to do this, they actually show the following. They show that if you take an unconstrained discrete Gaussian free field and you look at the minimum, if you don't constrain to be positive, what's the minimum? Well, the minimum on first order is 2 squared of g log n. So the reason that it goes up by 2 squared of g log n is kind of to make room for the minimum. So it goes up, and then kind of the minimum, at least on first order, as the order, the same. The first order is the same as the order of the minimum, and kind of makes room for the for all the minima of the field. Okay. And essentially, that's all that's been known about this problem. So this, in order to do this, they write this. This kind of started the whole business of looking at them. Well, this dating from that. There's been a lot of kind of work on this problem, and now we know much more about this problem. So in fact, we know that if you look at, I did it for the maximum, but the maximum and the minimum are the same. You know, not only it's 2 squared of g log n, the order of the minimum or the maximum, we also know the second order term. There's also convergence in law. So if you subtract this, then the maximum of the minimum converges to some limiting law that is kind of fairly well understood, and so on. So and there's more. We know not just the maximum, but all second maximum, third maximum, all the extreme values, large values. We know a lot about the extreme and high value scenery of the Gaussian free field, and the hope is that if we know all of this, then maybe we can improve this. But so far, this is still the state of the art. And so the idea is to actually, use. So this is kind of the beginning of this, the onset of this project of using whatever we know about extreme values to actually study the original problem. But as a first step, we do it on the tree, not on a planar domain. And you can ask why the tree? Okay, so the tree is much easier than planar domain on one hand, but on the other hand, it's actually very similar to planar domain. Now, which might look surprising because for many other problems, tree and planar domains are very different. For the sake of Gaussian free field, random walks, certain aspects of random walks, tree and planar domain are very similar, and I'll try to show this. So if you do the Gaussian free field on a planar domain, that's what you get. You get that it's a Gaussian field. The value of the vertex is Gaussian with variance g log n. G is some constant, maybe we should say. The covariance looks like this, so it kind of decays logarithmically. If you do this on the tree, we did this before, it's okay, this is Gaussian with 0n, and the covariance looks like minus, okay, so it's the common, it's the length of the common path, but you can also write it as n minus 1/2 the graph distance between x and y. And now, if you compare these two things, and you kind of replace n with 2 to the n, it begins to look similar, and the idea is that the log of the Euclidean distance is not very far away from the graph distance in a tree. For instance, if you embed the vertices of your tree on the interval 0, 1 or the interval 0, n, kind of you just put the tree and you take all the vertices and put them, put all the leaves one after the other, so that you have n points in the interval 0, n, then roughly the log of the distance between 2 points will be roughly the graph distance. So this. Okay, so Euclidean distance between an embedding of the points of the leaves of the tree. So the log of the Euclidean distance of an embedding of the leaves of a tree is kind of typically very close to the graph, or maybe half the graph distance between x and y. Okay, so these are not too different, and it's okay. That's actually the case. A lot of the results are very similar. So the idea is to start with this because it's easier to handle, and then go to this. And today I'm going to show you this. Okay, questions. Okay, and on the tree, we know at least as much as we know about the plane in terms of the Gaussian free field. Essentially, it's comparable. We know, as before, the maximum. This is the centering sequence of the maximum. The maximum on first order is square root of 2 log 2. That replaces the square root of 2, the 2 square root of g that we had before. There is a logarithmic. So before we had. On the plane, it was 2 square root of g log n minus constant log n. Again, the analogy is you take capital N and you change it into 2 to the n. So now on the tree, you get the order of the maximum is a constant times n minus a log n correction, and you know this explicitly. And if you take the maximum and subtract the centering sequence, you get convergence to the same limiting law, similar limiting law as you had before. Okay, so the order of the maximum or the minimum is linear in n. Yeah.
What is a limiting derivative
martingale? I won't be able to get to this here, but there is so if you are familiar with Gaussian multiplicative chaos or Louidor quantum gravity, okay, so all these are fancy names. So there is okay. So G is just a Google random variable. That's easy. Okay, some well-known distribution, and then you just this means plus independent. I don't know why I wrote this strange sign. But this means the G is shifted by, so you take a Google and you shift it independently by some random variable, and this random variable has some way, there is some implicit way of getting this random variable as a limit of some martingale that's associated with the branching random walk or the Gaussian free field on the tree, but I won't be able to get into this. But there is well-known, this one is a well-known object, and it appeared in many other places.
The question, so the 3 hacks instead of 3-4 is just because you have binary branching? Or
yeah, yes. I mean, if you had something else, yeah, that would have been something else and not, yeah. Not, yeah. You're comparing to the Gaussian free field. Probably you can do, yeah, probably you can, yeah, if you match the variance and take a 4-array tree, it sounds reasonable that it would be the same. Okay. So what is known about this problem? So, okay, again, the problem is study the branching random, what was our motivation? Study the branching random walk condition on all the leaves to be positive. So there are some asymptotics. From 2020, we have that on first order asymptotics. The first order asymptotics is 1/2 mn squared. Mn is the centering sequence, is this. So you square this on first order. I mean, it's the first order just gives you the log 2. So on first order, the probability of having all the leaves positive is this. This is reminiscent of the this problem that I showed you on the planar domain. This is kind of similar. So okay, this is similar to this. This is the same first order result of the probability that the field is positive for the leaves.
Except in this one, it's all of them, no?
No, it's just a leaf. You mean in the previous one? Yeah, you can put it, but it won't matter anything. It doesn't matter. If you change, you put this to here, and it will be the same. in the tree, sorry, in the domain, it will make a difference. If you insist that the Gaussian, I didn't say this before, but if you insist that the Gaussian free field on the box would be positive, not just inside, but all the way out to the boundary, then it's a whole different, then it's exponential in n, not log n squared. Because next to the boundary to have all, there's a boundary effect. You need all the things next to the boundary to be positive, so you're controlling n, essentially order n vertices, and it's like exponential in n. But here there's no such issue. And this was improved slightly by Roy, who showed actually that second order, second order is this, and moreover, so this was part of a large collection of results concerning large deviation principles for the minimum. And having everything positive is like having the minimum above its centering value, also above zero. Roy was actually more interested from the physics perspective. So he improved this constant and also showed that, as in the case of the Gaussian free field on the box, when you condition things, the leaves to be positive, the leaves live up much more. And they lift up, on first order, they lift up, as in the case of the planar domain, by the order of the minimum or the maximum. But then he actually showed that they lift up by less. Okay. I didn't say that here there are many questions. Let me go back to this part. And so there are many questions here that remain unsolved. For instance, second order terms here. Here, is this really, the lift is 2 squared of g log n, you lift up by 2 squared of g log n. What is the second order term? Okay. So this is just first order. The Gaussian free field lifts up. If you subtract the new centering, do you get the old Gaussian free field, or do you get something else? So all these are open questions that we'll actually solve in the proof. So, okay, so I think that's more or less the motivation in the setup, and now I can tell you some of the results. Okay, so the first, kind of as a side effect, this is not the important part of this work. We actually improved the probability, we find, or the asymptotics for the probability of this positivity event, of all the leaves positive. I sometimes refer to this as the hard wall event, because it's like putting a hard wall that kind of makes all the leaves positive. So, okay, so the first thing we do is just improve the asymptotics for the probability of all the leaves positive. In fact, we actually do it more generally. So I'll call omega nu the probability that, so typically the minimum is at level minus mn, that's its typical centering value. Now I want kind of this is the right tail of the minimum, and I'm interested in this probability for use, which can be as large, for instance, as mn. So that if I put mn here, I get that the minimum is positive. Okay, and so it turns out that this is the formula. This is the asymptotic formula for this right tail event. So the probability that the minimum is higher by u than its typical value is this. Okay, is this kind of explicit formula, and then there is kind of a strange function theta of bracket u 2. Now, what is this? So this would kind of appear everywhere here. So whenever I write the quantity bracket 2, I'll call it the log mod of u. So that's the fractional part of log 2 of u. And so, okay, and of course this is, okay. And so this somehow appears here. It's something between 0 and 1. So there is some function, some bounded function between 0 and 1 to r. So there's some kind of fluctuating constant. We don't know much about this. But that's the, okay. So
but it is not constant.
We don't know. It could be constant, it could be, we don't know anything about it. Or we don't know if it's continuous, we don't know whether there is a, we don't know anything about it, unfortunately.
It could be 0.
It could be 0. Comes up in the proof. So in particular, if you plug in u equals mn, okay, so you just plug in u equals mn here, and what you get, okay, so this is the original mn. For the rest of the talk, I'll need, ln will be the log 2 of n prime will be n minus ln, and then mn prime, okay, is just mn minus constant log n. Okay, and it turns out that, okay, the asymptotic on the log scale of the probability that all the leaves are positive is this. Okay. So it's 1/2, it's not 1/2 mn squared like the first order result, but rather you need mn prime, so you need to subtract from mn this constant log n term. I'll explain where it's coming later. Okay. And then in addition, there is some sort of potentially some constant that depends only on the log mod of n, only on the fractional value of log 2 of n, fractional part, times n linear n, the rest is little o. Okay, that's, as I mentioned, this is kind of a side effect. And now, okay, we're more interested in what happens, how do you get this event and what happens on this event. Okay, so okay, this is the same notation as before. I'm going to, from now on, I'm going to look at the, okay, I'm going to write p plus n as the probability conditional on this positivity event. Okay? And so it turns out that we know how the field actually lifts. Okay, so the first order result tells you that, oh, I didn't tell you anything. Sorry. How does the field realize this positivity constraint? Well, it goes at level up to the first log n generations, up to ln. It goes, so at the vertex in the first ln generation, at the vertex x, the mean of the field is going to be mn prime times 1 minus 10 to the minus x. So it kind of goes, I'll have a picture in a second. It goes all the way to mn prime. Mn prime is this mn minus a constant log n, exponentially fast in the first ln generations. And moreover, we even know the tails. So the tails, the lower tails are Gaussian, and the upper tails are almost Gaussian. Gaussian with some logarithmic correction. Okay, so maybe I have a picture. Here's a picture. So the field, the first log n generations, every vertex up to, among these 2 to the ln vertices in the first ln generations go up, and they kind of stay very close to this. Okay, they go all the way to up to a level mn prime. Okay, in particular, this is lower than mn. So the order of the maximum is mn. This is the order of the this is the order of the minimum. They actually go to a smaller. Okay, so this is smaller than the minimum would have been here. mn would have been here. Okay, so they go slightly smaller by precisely this quantity, whatever. This, okay, so it's C0 times ln. Okay, and they stay very close to this by up to an exponential, in a Gaussian or almost Gaussian sense. What about, okay, so this tells you about one vertex. In particular, you can show, so if you look at, in particular, the mean, that's what I said now, is not the mean height, that's true at generation ln, but it's also true at the leaves, and I'll have a sharper result later. In particular, at generation ln, they go up, the mean height is mn prime, so it's lower than the order of the minimum, and you have this Gaussian and almost Gaussian tails. Okay, so here's the picture. And what about, okay, so this result is about one particle. What about what about other vertices at generation ln? Well, that turns out that they're almost independent. If you look at all vertices at generation ln, they are all around mn prime, and the covariance between their heights decays exponentially fast in their graph distance. So Maybe the one next to the neighbor of a vertex in generation Ln is somehow dependent, but if you go 10 vertices away, then they're roughly independent. Okay, so here's the picture of the full. Okay, so you have all these guys following this trajectory. Here they're almost independent. Yeah, that's what. Okay, so that's kind of interesting, perhaps. But can we say more? Can we say something? So these are more like bounds. We don't know. We didn't say anything about the asymptotic law. So can you say something about the asymptotic law of this of this tree of the leads of this high field? And the answer is yes. Okay, so in the next couple of results, I'm going to tell you about asymptotics in law, and I'm going to discuss two types of asymptotics. Again, everything is under the conditional, under conditioning on things to be positive. So I'm going to talk both about local observables and about global observables. So local observables will be just the field after conditioning everything to be positive, the leaves to be positive, the field in a neighborhood, which can be pretty high, but not the entire, pretty large, but not the entire tree. So it could be linear in diameter, but not the full tree. And I'll also, okay, so we can handle this, and we can handle also global observable. So for instance, I would want to know, okay, I condition the field to be positive, what is the new maximum? What is the new minimum? What's, I mean, for people who are familiar with the subject, what about all the martingales? There's these exponential martingales that are associated with the branching random walk. What happens to them when I condition things to be positive? And so on. And the reason that we're going to separate this is that, okay, so there is a kind of, there's a different behavior, whether you look at local and global. I'll try to explain this. Okay, so we'll start with the local observables. Okay, and okay, so there are maybe two kind of difficult slides, but then it hopefully become easier. So okay, I want to talk about weak convergence. That's convergence in law. The problem is that I want to talk about convergence in law. Let me go back to the picture. Even I want to say that the law of this leaf here converges to some law. The problem is that the law of a vertex here will have a very large variance. It will have a potentially it will have like a variance. So suppose that this was a Gaussian with variance n, like in the unconditional case. Now, if you want to compare quantities with large variance, you want to say something about the limit law, you cannot use weak convergence. Right? So, for instance, if you take a Gaussian with variance n and mean 0, and a Gaussian with variance n and mean 1000, in the limit, their distance in weak topology is going to go to 0. So, if you want to kind of be able to distinguish order 1 differences in random variable which have unbounded fluctuations, you cannot really use weak convergence or Prokhorov metric, and we're going to use something stronger, which is called the Wasserstein metric. So in a sense, okay, it's okay. I'm sure you know. It's just so we're going to compare. Okay, so the Wasserstein distance, the P Wasserstein distance between two probability measures on the tree, is going to be the expected value of the pth norm of the difference in this of the uniform distance between two fields under the best possible the best possible coupling that you can between P1 and P2. Okay, I'll say this again. So I'm taking probability distributions on fields. The Wasserstein distance between two of order P between two such probability measures. What do? I look at all possible couplings of these two fields. Under this coupling, one of them would have law P1, the other one would have law P2. And I'm looking at the uniform distance, this uniform distance between the two fields. I take the pth moment, or and I take the LP norm. So the and the infimum of all possible couplings, that's the Wasserstein metric of order P. Okay, so So that's the buffer time, and I'll also do this in a local sense, which I'll call WP lock, which means that I do the same thing, but I just restrict to any finite neighbor. Okay. So this is a hard slide, and here's a harder slide, but the next one will become easier, I hope. So we want to say something about the limiting law of the branching random walk or the Gaussian free field when all the leaves are conditioned to be positive. Okay. So we have two main theorems and then some corollaries. The theorems are slightly they're more general, but slightly more involved. First of all, the first theorem says that there is a limiting law for the field condition to be positive. It's actually a family of laws that depends on delta. Okay, and if you test your field condition to be positive, under some set AN, starting from a leaf generation Ln, okay, and you subtract the centering value, this will converge in this Wasserstein metric to this law, to a field with this law on the same set. Maybe I'll show this in the picture. So we're going to, so here's the field. Okay, this is generation Ln. By this time, everybody here went to level Mn prime. And now when I'm going to look at the subtree here, okay, so if I'm looking at a subset An, let me connect it to this. So this would be my X or XLN. If I look at a subset, say this is my subset, this would be An. Okay, so if I look at the field condition, okay, so I take this and I condition all of the leaves to be positive, this roughly under the Wasserstein metric would have a law, okay, here's this little set An, would have a law of a field which is distributed like this P P plus, and what's okay, and this index delta is again this log mod of n. You can ignore this for a second. So in other words, we know how the limiting law, once you condition of things to be positive, we know how the limiting law looks like. It looks like this measure. Okay, so I'm telling you there is some family of measures. There is some construction of this measure. I'm not going to show you how this measure is constructed. So that's one theorem, a characterization, and you can do this very precisely. So you can take, as long as the set that you look, this target set which you compare, as long as the target set satisfies some growth condition, it's not too big, then you can compare the conditional field with this limiting. So maybe I'll write it like this. So this is this, and this is the probability of this P plus N2. It's rough. It's below 1 in this Wasserstein metric. So the first theorem is a comparison between the conditional law and this limiting law, this construction I'm not giving you. The second is a theorem that tells you, okay, that's very nice, but how does this help us? Well, I'm going to tell you some properties of that limiting law P delta, and there are various properties, but one important property is that if some sets satisfy, if this is small, but it's again a general statement. The next slide will give a simpler corollaries. But if your set if you have a set such that this is small, then you can compare this guy to the usual Gaussian free field or branching random walk, just shifted globally by a random quantity that's dependent of it. Okay, so this tells you if your set satisfies a certain condition such, or a sequence of sets such that this is goes to 0, then this limiting law looks like the usual Gaussian free field, okay, shifted by a global quantity. Now, okay, how does these two things work together? So here's the first corollary. It tells you that if you take the Gaussian free, so what this tells you, the following is that it tells you in a local sense, this limiting measure captures what happens here in a local sense. It tells you that you look at finite dimensional distributions in the Wasserstein metric, the branching random walk condition on all the leaves to be positive looks like after you recenter by m and prime, then you get precisely this limiting measure p plus. So this limiting measure with a corollary. So this in particular means that this convergence happens in a local sense. Okay? The limiting measure captures, so there is a limiting measure in the sense of finite dimensional distribution, oops, and this is this limiting measure p plus delta. So there is a limiting law. Okay. I think I have a picture in a second. Okay, I'll show you in the picture. And more, okay, so that's one corollary. Another corollary is that if you look next to the leaves, okay, maybe I'll draw this in a picture. I'll show you a picture. So these two theorems say the following. It say that if you take the branching random walk condition to be positive, locally, in terms of finite dimensional distributions, what you get here, so you take any finite set of vertices, what you get is convergence to this centering, so everything is going up by m and prime, plus this limiting law p plus delta, which only depends on this log mod of n. Potentially, again, we don't know. Maybe this doesn't exist, and there is they're all the same. So, but our proof gives a dependence on the log mod of n. And moreover, and that's the second. This is the second corollary. If you look at the piece next to the leaves, the piece is not too big, so there is some condition. Some radius here that depends on the pith order of your Wasserstein metric. So the more you require, the smaller the diameter of the region that you're looking at becomes. But it's still linear. So if you look at the piece of your branching random walk condition to be positive, what you get is m and prime. Okay, it's shifted by m and prime. Regular Gaussian free field, but started from here, not from here. Plus a global shift. So if you look at this guy, it's just a regular Gaussian free field, slightly smaller in number of generations, and shifted up globally by a dependent quantity, non-trivial quantity. Okay. In particular, if you would look at the differences, so that's this guy. If you look at the differences, the gradient, so this will disappear and this will disappear. And it doesn't matter if, once you look at the difference, it doesn't matter if you look at n prime or n. So if you look at, so the gradient of the field condition to be positive looks exactly like the gradient of the Gaussian free field without condition. But so for the sake of the gradient, it looks exactly like without conditioning. But otherwise, it doesn't look like the Gaussian free field. It looks like Gaussian free field on a slightly smaller tree and shifted globally. So this answers the question of how does the field look like when you recenter it, but in the tree case, not in the...
The random shift is supported.
Say again?
The random shift is supported in some particular, like positive values.
Positive. I have to remember, I think maybe positive. Maybe not.
But that distribution is well described.
Maybe not positive, actually. Sorry, not positive. I think but it's okay. Go on.
Is explicit or is
it's not really explicit.
Okay. So it comes from the construction.
It comes from the construction of the law. Yeah. I can tell you exactly how it's constructed later. Okay, so that's the picture. And
is it related to like some derivative martingales?
No, it's actually not that complicated. But I want to get to some more results, and maybe if I have time, I'll tell you. So what I want to do in the next 10 minutes that I have, I won't be able to get to the proof, I think, but I want to give you I want to tell you some global results. So these are local. So locally, this is how it works. So there's a limiting law in the sense of finite dimensional distributions, and next, if you're looking at the neighborhood large but not the entire tree, it's a usual Gaussian free field shifted random. And I'm going to switch to global results. That's one thing I want to tell you, and then I'm going to tell you a little bit about how why you get this picture. So let me switch to global observables. What global observables we're going to look at? So maybe the simplest one would be just the empirical mean of the tree. So you just look at the average over all leaves. If you take a branching random walk and you average over all the leaves, you get a random quantity because the beginning of the tree matters. Here you don't. Here you get a constant. Under the conditioning, you get essentially you get mn prime plus this kind of strange quantity. I don't know what this is. Okay, you get mn prime plus plus some quantity. I didn't tell you what this is. Plus some potentially fluctuating quantity, but a constant value. Essentially, you get the same. Fine. So this randomness disappears. What about the maximum? Okay. So maybe I'll switch to the picture before. So here's a bunch of them, and you can ask, okay, now condition everything lifted to mn prime. What's going to be the new maximum? So you can guess various things. You can guess maybe that the maximum would be, okay, if it went up by mn prime, maybe the maximum will be now 2mn prime, so mn prime plus mn prime, or you can maybe guess that it's mn prime plus mn plus the usual order of the maximum, and both answers are wrong. It's something that's, okay, so this is the precise value, and it's something that's smaller than mn prime plus mn, but larger than mn prime plus mn prime. Okay, and another important thing, if you subtract, you get convergence to Gumbel, but no random shift. The random shift disappeared. Okay, so this effect of conditioning things to be positive kills a lot of the randomness. Okay, kill the randomness in the empirical mean. It kills the randomness in the new maximum. It will also kill the randomness in the minimum. If you look at the new minimum, okay, here things are completely, are very different. For the unconstrained field, it's Gumbel, as we said. Of course, for the constrained field, it cannot be it cannot be negative. In fact, it behaves, there's a scaling limit to an exponential. So it behaves like 1 over n. Again, there's kind of this strange fluctuating mysterious constant, but otherwise it behaves like 1 over n times an exponential. And lastly, for exponential martingales, for people who are familiar with branching random walk, if you take a usual branching random walk and you look at this guy, this is a martingale, so okay, you just essentially divide by the mean. So this is a martingale, and these are called exponential or additive martingale. They play an important role in the theory of branching random walk and Gaussian free fields, and they converge to a limit law that depends on, it's an exponential of the value of the field at level alpha. Okay, so you go over all the leaves, you take the exponential alpha times the value of the leaf, and you just divide by the mean, and then you average over all leaves. This, as I said, this gives you a martingale. Okay, it's a non-negative martingale, so it will converge to a limit, and you can even show that potentially, you can show that the limit is non-degenerate, and you call it Z alpha. So that's the unconstrained case. Constrained case, you get a constant. Depends on alpha, potentially on n, on this log mod of n, but there's no, this is a random variable. The limiting derivative martingale is a random variable. Here there's no, so again the randomness disappears. Okay, and I think, okay, so overall this just says that the unconditional and the conditional field are very different, and the laws are asymptotically mutually singular with respect to each other. Okay, I had about 5 minutes. Okay, let me tell you a little bit about the proof. In 5 minutes, that's kind of more or less going to be enough. In particular, okay, I won't be able to. So what I want to kind of explain is why this field lifts to mn prime and not mn. Why? Okay, so the order of the minimum is mn, but it actually lifts to slightly less to mn prime. And what happens? And why do you get all this loss of randomness? Okay, so the kind of the beginning is to try to understand this event, this right tail event. I'll do it generally for any u. In the end, we'll plug in u equals mn to get positivity. And clearly, if you want to get your minimum, shift your minimum by u up, you better do it very quickly, because the more you wait, the more particles or the more vertices you have to control. So one option is to just take the first generation, the first kind of first generation, and lift everybody by u. And so if you lift if the two childs of the root are lifted by u, then you're done. Okay. However, this might be costly because you're controlling, because you need to take two centered Gaussians and lift them by u. And maybe if you wait further, if you control the leaves at generation k, now each of them is a Gaussian with variance k, so it's slightly easier to lift a particle or a vertex at generation k by order u. On the other hand, now you have 2 to the k vertices. So there's kind of a competition between, okay, so on one hand you want k to be small so that you have less particles to control. On the other hand, you want k to be large because there's more steps and you have more variance. It's easier to lift your variance. And one way of doing this, and it's kind of a standard way, that's also how they did it in the planar case, is to kind of just look first at the energy term of the Gaussian free field. So this is this was the exponential that appeared in the density. And okay, and you want at 0 so at 0 you're 0 because you start from the root. You want the generation LK, you want to be u. And now, okay, you want to optimize. What's the optimal profile? What is the optimal way to assign heights to the vertices up to generation LK to get from 0 to u and minimize this gradient? That's what appears in the density, and that leads. Okay, so this is a well-known name. It's called the capacity, or u squared times the capacity. Okay? It's the kind of the optimal function that gets from 0 to u and minimizes the gradient. It turns out it's the harmonic extension. It's an harmonic function, discrete harmonic function that starts from 0 and ends at u. So that's what I'm saying here. So it's an harmonic function that starts from 0 so it's harmonic, it starts from 0 and it ends at u, and that gives you kind of the first order asymptotics of this course. Okay, you can compute this, and you can see that this is if you follow this, you can see how this harmonic function looks like. So this harmonic function goes from 0 to u exponentially fast. And this is what you have to pay. That's the cost. And that's true for any case. So you can, so no matter, as long as k is bigger than log 2 of u, if I'm looking at the harmonic function, or if I want to minimize this quantity, okay, as long as k is bigger than log 2 u, this is so this is the profile, and this is what I pay. And now you just take the minimal k. You can see from that there's no point. I mean, the energy stays, or this stays 1/2 u squared. So there's no point in taking a large k, because that just means controlling more particles. Okay, I'm kind of hiding slightly things. And so you realize that, okay, so you do this kind of first order, and that's been done also in previous works. You're doing this first order analysis, and you realize that the optimal way for the field to go to level u, or to lift the minimum by u, is to go in log 2u generations all the way to level u and do this in this exponential way, following this harmonic profile. Okay, so that's okay. So that's what you do. But then and that's kind of the one main idea that in this one important realization that one has to make is that once you did log 2u many steps, okay, you've also shortened. Look at the picture. So once you do this is okay. Let's do this for mn. So we know the optimal way to get to get here to level mn is in log n generations to reach height mn. That would make everything positive. But then you realize that once you did this log n generations, you've shortened the tree. If you've shortened the tree, then the minimum became slightly smaller. Okay? Maybe I'll go back to it. Right. So if you wait log 2u generations, the tree has been shortened by log 2u. So that means that the minimum of the tree is no longer mn, of all your subtrees are no longer mn, but mn minus whatever number of generations that you take. So then you realize that you actually don't have to go all the way to log 2u. You can actually, so you don't have to go to lift everything by u. You can actually lift everything by u prime, which is this u minus this log u generations, because by the time you do this, the minimum has already decreased because the tree has shrunk. Okay, and that explains why you don't get mn but mn prime. Mn prime is precisely mn minus c0 ln, and again the idea is that your first attempt is to go all the way to level mn. But the optimal way to do this is in log n generations. But by the time you do this, the remaining number of generations have also decreased, and so that means that your minimum has decreased by log n. And so that means that in the first place you don't have to go to mn, but you can go to mn minus this log n, and that gives you the mn prime. And I guess this is all I would be able to say. Just a little bit more, but yeah, okay, I'll stop here.
Oren, any questions? But so essentially, when you average out with this conditional measure, you get this small O of 1. Is that will you get like a GFF story out of there, or like a normal when you properly renormalize the story?
You mean the average of the empirical measure?
Yes, the maximum.
I mean this one or this one?
Yeah, the one where you were doing, yes. So I could just look at the O1. So does this O1 here become like a Gaussian when you properly normalize?
So the picture is very simple. Let me show you. Let me explain you the picture, and then we can find it together. Oops, here's the. Okay, here's the picture. So. Okay, because of what I just explained, conditional on everything being positive, all the particles here lift to level mn prime, a little less than mn because the minimum is already small. Now you have a bunch of particles here. They all start from a height which is where the typical minimum is of order 0. So the typical, if they start from mn prime, and the typical order of the minimum is minus mn prime. So if you start from that height, the typical minimum is 0. So for these guys, the conditioning is you condition on something very typical for them. It's not singular. Moreover, they're almost independent. What I mean by almost independent? So maybe these two will be dependent, but the covariance decays. So they're order 1 in terms of fluctuations, and the covariance decays exponentially fast, depending on how far the common ancestor is. So now you have essentially a bunch. That's why all the randomness is gone because you have a bunch of independent. You have n many of them because 2 to the ln is of order n. So the picture is very simple. You have essentially order n branching random walk conditional on a typical, on the minimum doing something typical, but you're conditioning on something, it doesn't disappear. So conditional on a typical value of the minimum, and they're almost independent. So that gives, so that will give rise, I'm pretty sure that, so that should give rise also for central limit theorem. I don't see, I don't see, and moreover, there's a limiting law. Maybe I didn't say that. So there is a limiting law. So the law here, if you take n to infinity, the height, each of them has a marginal with the limiting law. And so the answer is, I think the answer is yes. Again, you have to get rid of that. I mean, there's dependence, so you maybe have to cluster a few of them together. But otherwise, there should be a CLT for this.
The second one is, can you give an intuition on why do you get the exponential for the minimum?
Again, if you look at the, it's kind of from so it's okay. If you draw right, so relative. So again, the minimum is typical for a random branching random walk that starts from here. So okay, so the minimum is a random variable, and you condition this random. Okay, you condition this random variable to be positive. It's an order 1 random variable because the minimum typically is order 1 around its centering value. And so you have random. So at the end you have order n random variables, all order 1, and you condition them to be positive. And so it's like the minimum. Okay, it's like the minimum. You have a minimum of essentially absolutely continuous random variables, which are all supported on the positive half line, and they all have density around 0, and that will lead to always to an exponential. So it's kind of like the minimum of n uniforms. More or less the same as having n uniforms on 0, 1, 0, 10, I don't know, and you're looking at the minimum. They would have that will decay. The minimum would be of order 1 over n, and if you scale by n, you get an exponential.
Thank you. So it was, I didn't realize, so it was renormalized.
It was not renormalized, just recentered.
It's 0. I mean, go
to 0,
and then you have to, okay, I didn't.
Yeah, so I have a question. So what about this beta random variable? So you said that somehow like
so yeah, I can explain. It's very simple. So okay, so how to get how?
Yeah, because usually this random shift comes from the beginning, right? But the beginning here seems to be pretty strict.
So what is this eta? So at the end you need to, so for all these local observables, what makes them local is that they actually belong to exactly one subtree and not more. Once you get more subtrees, you need to use the almost independence, and it's a different analysis. Local observables, what makes them local? In particular, they belong to exactly one subtree, so you just need to analyze one subtree. So you're in this picture. Okay. So okay, now how does this law looks like? It looks like you know that there is a limiting law here that you do by okay, that's okay. That's a theorem. So you have a branching random walk that starts at a height mn prime. Around the height m and prime according to some random law, and it's conditioned to be positive because the conditioning remains. But again, this is a typical conditioning for such a branching random walk because well, for such a branching random walk, the order of the minimum is minus m and prime, and you start from m and prime, so you're just conditioning the minimum to do something typical. And so now you have to analyze the branching random walk condition on its minimum to be positive. And it's not difficult to see that okay, you don't get rid of this, you never get rid of this conditioning. So if you condition the minimum, because you're still conditioning on the minimum to do something, but far away from the beginning, and but if you look at the neighborhood which is not the entire tree, maybe something like this, then the effect of the conditioning is just an effect of a random shift, and this is where these etas are coming from. The way we do this is we construct a coupling between the usual branching random walk non-condition and the branching random walk condition to have a typical minimum, and you can show that you can show that the difference between them is a field which asymptotically, if you don't look at the whole field but you look at the limited region, becomes a constant, and this constant is the eta. But the short answer is that if you take a branching random walk and condition to be condition its minimum to do something typical, then if you don't look at the whole tree, on a subset of the tree, it will just look like the original one shifted globally by some quantity. And this quantity comes from the beginning, but
from the beginning of the second part.
From the second part, yes. That's it. Yeah.
One more question. So I guess that you can also look at the extremal process.
Yeah.
Of this. And
to look at the extremal process of regular. So again, what happens now is that
there is no martingale anymore.
There is no derivative. So it's just the external. You essentially have. There's a bunch of each of those. Okay. It's a bunch of independent. It's a good question what you will get, but you will lose the derivative martingale. So each of those will give you some sort of. No, but I mean the point is that also why you get that the law of the new maximum is okay. I don't know what's written here, but it's probably the wrong. So you get okay. So what is the new height of the maximum? So now you have a bunch of n independent branching random walks. Each of them behaves okay. So there's it's conditioned to have its minimum to be typical. That really doesn't affect almost. I mean, it affects only very little the maximum. And so now you have a bunch of independent branching random walk with their typical maximum, which is this shifted Gumbel. But you have n of them, and this shift and they all have the same tail. Oh, sorry, they all have the same law. This shifted Gumbel, but it's okay. This shifted Gumbel is still an exponential tail. So essentially, you have now a maximum of n exponential, exponential random variable with an exponential tail, and that gives you a usual Gumbel. Right. So you average. Okay. So you. You look at the maximum of things that have a random shift, but then the random shift disappears. And so I guess the external process will behave the same. Look like an external process of a usual of the exponential random variable. No random shift.
Okay. Then more questions. That's Oren.